So now in this video we're going to take a quick look at this, it's a buck converter, but it's a USB buck converter. So it outputs USB 5 volts right there. It takes in a higher voltage. We just clamp this to a higher voltage and outputs a lower voltage. So that may sound silly, you got a lower voltage out, but we don't have to provide as much current coming in as we will get out. We are going to power the unit with this power supply here. We have the alligator clips there. I can just clip these alligator clips from the power supply to these. These are large though, so they would clamp onto a big battery cable or something really easily. But for this video, they would also short circuit easily. This has short circuit protection, but I'm going to try to be careful not to ever let them come into contact with each other. So now just powering the unit at 10 volts, and I don't know how close we'll be to get that, we can go down to 8 volts up to 35 volts right there. And if we go any below 8 volts, you can see it turns off right there. That's a low voltage though if you are worried about a battery. So don't use this to try to shut it off with low voltage to protect the battery unless it happens to be under 8 volts. Now here we have a little, it's kind of like a multimeter. We can look at the voltage and the current in real time. You can also look at the power calculations, and also it's going to, okay, it didn't reset it because I think I don't have a load again, but you can also see capacity, so how much current flowed over time, and power if you want to. But in any case, let's just look at voltage and current for now. So we got 5.23 volts. That will probably go down as we draw current. But there you can see it says 0 amps of current right there. But we got 18 milliamps, 0.018 amps. So we already have a current. Most of it's for powering this, and a little bit less of that is for powering this. So we're never going to get, like when we powering something at 5 volts, it'd actually be slightly higher. But if it were 5 volts and we got 10 volts, it will never be half the current that is actually being supplied from the power supply versus what we're getting at the load, because that's using some of the power, as is this. Keep that in mind. And now we'll get to the actual test. So I already plugged in the USB there. We could go up there or down there. Somebody suggested just do the output there if you're worried about something taking data off your phone or something. And I thought that was a good tip. So let's plug that in. This is about 51% charged, so it needs to charge pretty badly. It's accepting about 2 amps of current at 5 volts right there. You can see that the power supply is providing 10 volts to power all of this. And it's close to 1 amp. It's a bit higher right there. Again, it's not going to, that needs some power, and so does the buck converter, and also there's losses. It's not 100% efficient right there. So you could probably get a better buck converter that's a lot more efficient. But you can see as we go up in voltage, the current we need from the power supply goes way down. And, you know, we're a little more than 1/4 of the current from the supply as is being output. But again, we have higher voltage in, lower current out, and we can go up to 30 volts. This particular power supply has a power limit, so at 30 volts, we can only provide a maximum of 1.66 amps right there. Because it's higher voltage, more current, or the same amount of current is higher power, it creates more heat. So when we raise the voltage there, we got to lower it there. So I thought I would just mention that. But in case, there we go. We got about 1/5 of the current coming in that we are getting out. So math is not adding up here. It's not as efficient. We could test out all that stuff, but that's probably pretty boring. So we're not going to worry about that. We're just going to move on. And as another example, we have the portable fan here, which has 18650 batteries in them that I've been using for a bit, so they're recharging. So you can see the current paths right there. We'll go up to, let's do 20 volts, and then I'll turn the fan on full blast. It'll probably give a whine, and okay, it's less current, so I thought it might be more, but in any case, we can change the current load there. You can see it in real time where the power we need to provide this power out is changing as our power needs change. So now we come back to the diagram. I looked at this unit in a few videos earlier. I don't think I ever did a diagram. If I did, I hope it wasn't better than this, but I didn't look. But in any case, we got that higher voltage coming in. Doesn't matter where the source is, what the source is. I have lithium iron phosphate batteries, so at some point we're probably going to hook this up to one of those. And they have a nominal voltage of 12.8 volts, but it's usually higher, especially if you don't use it much and you charged it. So in case we got that higher voltage coming to the buck converter, we got the lower voltage out. We saw that. That should make sense. We also monitored that voltage. So these two took power to power them. So that all, of course, is going to come from the input there. So the current that it needs to provide is going to be higher than what we would calculate. And so we got the load there. And when it comes to converting the power to, it's not 100% efficient. So I think with this setup, we're probably getting like 85% efficiency. If we got rid of this, you know, maybe it'd be like 90% or something efficiency for this. I don't know. Those are tests we could do, but we're not going to do in this video anyways. So we saw pretty close to this, 5 volt, 2 amp. It was actually slightly above 5 volts, but slightly below 2 amps. So I think power-wise, it came out to this really good. And so with the input there, when it was 10 volts, I believe it was like 1.15 amps. Not exactly 5 amps, but in that range. And so I think that's about 85% efficient there. When you take those two numbers, 1.15, that's a bit higher than what we expect, but not a ton, you know, maybe 10-15%. And then we got 15 volts, about a third of the current in that we were getting out, but 3 times the voltage. And this probably wasn't as efficient because as you get further, or a bigger voltage difference, I should say, the more the voltage difference is, probably you're going to have more losses. But in any case, we were, you know, relatively close to 0.66. It's probably like 0.7. And then 20 volts. I think we're getting really close to 0.6 amps there. But again, not terribly far from 0.5 amps. And that's a fairly big voltage difference. So we probably had more power losses in the conversion right there. And so the 1 amp, the math's really easy there, half, 0.5, a third, 0.333, and then a fourth, 0.25. So 4 times the voltage coming in, a fourth of the current needed for the current that you get out. I added a note down here. So one reason why you might do something like this, you may have a load that needs like 5 volts. A fair distance away from it, you have a higher voltage power source. You don't do the buck conversion near the power source, you do it near the load. That's because voltage travels through wires really well, no matter what the resistance they have and stuff. But the more current you need from them, whatever the voltage is, does need thicker cables because the resistance does really build up when it comes to how much current is flowing through there. It creates a lot of waste heat, a lot of waste power. And so you can get away with smaller wires if you have a higher voltage, as long as the insulation is rated to handle the voltage you're going to use. So when it comes to battery systems, I don't know how dangerous 48 volts is, but that's kind of the limit people set when it comes to safety is 48 volts. You may still get shocked, I don't know. But a lot of systems have that. So you got that higher voltage from a battery or whatever, it may have to travel a while. That's fine. You just put the buck converter really close to the load, and so that energy will travel over the long wires as voltage, so you're not going to get much power loss because it's a higher voltage. And then you'll have thicker cables going to the load because more current's going to flow through them, and the thicker the cable, the less resistance it has, so the more easily current can flow through it. Hopefully that makes sense. So that's really about it. The meter, USB meter, was voltage, V, I current, P for power, and C for capacity. So if we were powering something for a long time, again, let's say we got that battery and we knew it's 7 amp hour batteries, the ones that I have, and so 12.8 volts, whatever that watt hours is. If we don't have a battery monitor, we could look at how much power this was using up over time. So it would be the capacity, the amount of current times 5 volts there. And when those numbers start getting close to the maximum, then you could cut power or something. That's one use you could use for this if you really wanted to. But again, that's topics for other videos. We're going to end this one here. Thanks for watching.